Hello, I'm Milana Nazarenko. I'll be talking about alcohols, epoxides, and ethers, as well as our Grignard reagents and kind of doing a product prediction of some of them. So I'd like to start off by sharing my screen and going back to what Dr. Marshall showed us in Module 7 on the last video in our notes review. She did a very good job at showing us this video, this chart here. So I know it's kind of busy, but bear with me. I ended up adding a few little notes just because I'm more of a visual and colorful person, as you can see here. So I really like this chart because we're able to see that with a generic alcohol, we start off here with. Let me see if I'm actually, oh, okay, we're actually working. Last time I recorded a video and I had to redo the whole thing. Anyways, so if we react with PBr3 over pyridine, we undergo a substitution reaction to form this alkyl halide of RBr. Then we could also react with either of these to form another alkyl halide through a substitution reaction. But the other product would have, other reactant would have been the PCl3 or COCl2 or SOCl2 over pyridine again to undergo that substitution reaction. Our preference for this type of reaction would be a second degree alcohol. So this next reaction that we have here is creating an alkyl halide with an associated halide acids. So these are our halide acids. The ones that we prefer would be the iodide, bromine, and chlorine in and under heat. These are the triangles for the heat. So in this type of reaction, we'll be undergoing a carbocation formation to then end up forming these alkyl halides here. The preference for this type of reaction will be starting off with a third degree, followed by a second and first degree alcohol. Our rate of reaction would be from an iodide, a bromine, and then this chlorine here. So to further go to our next reactions that we have here, we'll actually be forming ethers under both of these conditions. But we'll start off with this one here first. So our generic alcohol can react with itself in heat conditions to then form an ether, R prime O over an R. This will be called a Williamson ether synthesis. So the next condition to end up forming an ether would be an alcohol reacting with an alkyl halide to form an ether here. So again, the same type of product will undergo a substitution reaction of the halide, of the alkyl halide, and then our H of the O would also get substituted. So our next product prediction would be this alkene, and I like to call these conditions. So if you're in any of these conditions, you could form this alkene. It's just a better way of thinking it for me. I just hope I could pass that along to you guys. So we could form an alkene with the reaction of an alcohol and PCl3 over pyridine in cold conditions. Then we have a H2SO4 in heat, as well as H3PO4 in heat as well. Both of these here, I've marked that they are acid dehydrations, and I actually have an example of this one. So then the next condition that we'll have here would actually probably look more like this with a little arrow, but it could be pyridine over the negative CO3, H3, or TOCl3 over pyridine over negative OCH3. Again, the preference is 3-2-1 in our alcohols. It just works a little bit better when we form it this way. I'll go back to this example after I finish this chart. The next ones that I like to go over would be our, it'll be our alcohol reactions under these conditions if we are a first degree alcohol, and under these conditions, we will form a aldehyde. If we further oxidize, because this is an oxidation reaction, we will form a carboxylic acid. And I think Professor Marshall ended up telling us that if there's a one equivalence or if it's more than one equivalence, then we end up forming more. Or if it's still available, then we could form that carboxylic acid. So the other condition would be is if we're a second degree alcohol under these conditions here, then we could form a ketone. Very specific. So we kind of got to watch out for that. Might be helpful when we write it down for our exam that we have coming up. So the next thing that I wanted to share with you would have been that what's it called? The practice questions, or I guess I kind of went over them. Let's go back this way. This one? Yes. Okay. So I said that I had an example of that dehydration reaction. So what ends up happening is in a dehydration reaction in acidic conditions, where's my little crayon? Under acidic conditions. Okay, there we go. Under acidic conditions, which is going to be our strong acid and heat, if I'm a second degree alcohol, I'll form this cycloalkene with water. When we undergo this process, we end up forming a carbocation right here, a carbocation intermediate. And because of this, we have to watch out for rearrangements. That being said, that means that we could have a little formation of an alkene here or here. And I think in some very, very minor or off cases, we end up forming here or even here, I think. Then if we have a third degree alcohol, which we know that this is a third degree alcohol because we have our little alcoholic group attached to 1, 2, and 3 other carbon groups. So if I'm a third degree alcohol undergoing strong acid and heat, I will form a major and minor product. We follow Zaitsev rule with this. So a more substituted will yield us a more stable and major product, whereas a less substituted will give us a less stable and minor product depicted here and here. The other examples that I wanted to show would have been this acidic condition, just kind of quick little straight to the point overview. Again, reiterating, first degree alcohols will give us that aldehyde or carboxylic acid. We have to have this oxidizing agent. Our oxidizing agents are here and also previously listed on the chart before. And again, if I'm a second degree alcohol undergoing oxidation, I will form a ketone. So the next thing that I wanted to share with you guys would have been undergoing our ethers. So with our ethers here, let me get another marker again. With ethers here, we could form an alcohol with an acid here. We ended up forming ethers on both sides of the alcohol. So we get an alcohol with a normal one, and then our prime with an alcohol. This is under a first prime condition. If we further react with more, so if it says excess or if it's like 2HI or something like that, then we'll further form an alkyl halide right here. So the next thing that ends up happening, or that can happen, is an ether can react with 2HBr to form an alkyl bromides and water. Bromides and water. If we have an excess, and it'll be explicitly told if we have an excess of it, then we will form a alkyl bromine, and then we will also form that alcohol, the alcohol will go to the less substituted side, and then the more substituted side will have that bromine. Kind of a little reiteration, Dr. Marshall ended up telling us how one equivalent of HBr will force us to actually physically pull out the alcohol and the alkyl alcohol. This is done through an SN1 reaction. I have a little example here. You could follow through this little reaction here, and you end up forming this little light purple product. And if you keep on further reacting with HBr, then you end up forming that alkyl halide, and then this addition with water. And there's a little bit more written here. The next thing that I wanted to mention would have been an ether can also react with a sulfuric acid. So the less substituted side will get the alcohol, and then the more substituted side will get the alkene. These are just, again, some of the conditions that we talk about to get a general idea of what's going on. The next side that I want to talk about would be my epoxides and how rings break in acidic or basic conditions. So let's find it. Okay, so our epoxides can be undergoing a basic condition. So that could be a metal and a sodium methoxide acting as our nucleophile. Kind of a general rule of thumb would be if we have a metal, it'll act as a ion. So this will be a negative ion here. This negative ion, the oxygen here will end up attacking the least substituted carbon on this epoxide, and that's kind of where our break will happen. Our less substituted side will end up getting this sodium methoxide right here, and then our more substituted side would end up getting this little alcohol here. There we go. Then if we undergo acidic conditions, I ended up drawing it a little bit smaller, pardon me. So an epoxide can undergo acidic conditions, which include these little guys here, HCl, HBr, HI, or water and alcohol with acidic catalyst. So what ends up happening is our little oxygen here, he ends up attacking the hydrogen to break the bond between bromine. This bromine will basically be floating around until it is given the chance to attack this more substituted side. This more substituted side will be where the bond breaks, and it'll form this little molecule here. Yeah, the oxygen is on the less substituted side, so the hydrogen will attach to that. Generally speaking, epoxides are more reactive than ethers due to the strained ring. If there's a nucleophilic attack, it will open the ring. That's where we undergo our acidic or basic conditions. The other thing would be that ethers are very bad leaving groups, so they're generally unreactive. We have to add an acid in order for this process to end up yielding any products. The other thing that I wanted to show, oh wait, I already went over it. The last part, I guess I could show would be our Grignard's reagents. Just share that screen, maybe. There you go. Okay, so undergoing Grignard's reagents. So the reason why it's brought up is because we form alcohols. We form second and third degree alcohols if we follow these reagents. So the reagent here would actually be something like magnesium bromide. Right here on the bottom, a magnesium bromide over a hydroxyl, like acidic condition, which is going to be our workup. this workup will help protonate that alcohol. So we have our molecule here. I'll start off with number 2. We have a molecule here that ends up attacking the little ketone here. This ketone kind of forms a new molecule. So then this little guy ends up attaching where the break happened. Once the break happens, the oxygen ends up getting a negative charge. It needs to undergo a acidic workup and get protonated. Ends up turning into an alcohol. Or protonation ends up happening right here. It undergoes it, the electron drops off onto the oxygen and kind of goes away. This will be our final product as well. We end up forming a chiral racemic mixture and a 3rd degree alcohol. And then we could also kind of look at this 2nd degree alcohol formation. We have CH3 and magnesium bromide, which is our Grignard reagent. It undergoes these acidic conditions to then form a protonated alcohol. We take away the ion and end up forming this pent-2-ol racemic mixture, and we end up forming this 2nd degree alcohol, which are enantiomers. Kind of little quick facts. I thought it was interesting. This reagent was discovered in 1900s by Victor Grignard, who actually ended up winning a Nobel Peace Prize for it in 1912. He actually used it in his writings for his doctoral paperwork, and it ended up 12 years later in Nobel Peace Prize. So basically, we use a ketone to form a alcohol. That's what that is. Thank you for listening.